I'll start.
Yeah.
Okay, so yes, I should apologize in advance. It's a slightly technical seminar, but please stop me again at any point and ask me questions. I will at least try to communicate the basic idea behind this sort of new geometric approach to compute S matrices of in local quantum field theories, and hopefully convince you that it's a direction to understand S matrices of quantum field theory, which is worth exploring. Let me first start with a basic geometric idea that I will try to clarify, that this entire structure, so usually when we do S matrix theory, we start with a Lagrangian, which is some function of some fields, and then that gives us rules which we call Feynman rules, and then we compute the S matrix, by which we mean that there is a fundamental operator in our theory which is defined as time ordered exponential of the interaction Hamiltonian, and then we compute its so we computing S matrix really means computing matrix elements of this operator into arbitrary in and out states. And typically this thing, of course, because if we are in Minkowski spacetime, this thing will always have some universal factor which is total momentum is conserved, and then we will get some functions of external momenta. Suppose I have total number of momenta which is n, then I will get a function of this momenta which will really be a function of okay, if I have spin, then it will of course also be function of, say, polarization data, say if you have gluons, and whatever this thing is, it will always be a function of Lorentz invariant variables that you construct out of this thing, and this is called amplitude. And so the usual way to do compute amplitude is via starting with the fact that there is something more basic than S matrix, which is a Lagrangian, which tells us what the field content is, means what the kind of particles are and how they interact with each other, and that combined with the definition of this operator, we just we get amplitude. So this is the standard approach that, of course, all of you in Q of T books will also study. And now over the years, there's a long history of this. One of the big questions that has always plagued this subject is that in the end, when I look at this object is always some arbitrary function of, as we discussed, Lorentz invariant momenta, Lorentz invariant quantities such that, say, scalar product of momenta or scalar product of polarization if you had any, or a product of pi dot epsilon j. And of course, it will be, if you have done, I think most of you would have done computation of S matrices, it will be some very complicated function of, it will be a very complicated function of these objects with a lot of singularities in the, if you complexify these objects, then it has some singularities which are different for different theories and at different order in loop expansion. So one of the question which has plagued this subject is like, if I give you an arbitrary meromorphic function of this data, so I take these objects, like let's call these variables, xij, let's call this yij, let's call this zij, and suppose I consider this function, you will see that it typically has some singularities of very complicated sort in these variables xij. And one of the questions we have always been interested in physics is that if I give you some function, which is some functions of these variables, how do I know that it's the amplitude of some local unitary quantum field theory? So that yeah, no, just meromorphic or more complicated. So with branch cuts, etc. Any general function with singularities. So one of the problem has been, it's like a classification problem. If I give you a function with lots of branch cuts and poles, etc. of these variables, can I work backwards and deduce that it is actually amplitude of some local and unitary quantum field theory? So what I'm going to tell you today a little bit is geared towards making some progress in this direction. And the progress comes from a very different perspective, which has been quite puzzling and interesting in some sense. And the idea is the following, that let's start with a simple example where we have the only external data are momenta, no polarization or anything. So let's take simple that we are interested in functions which are functions of Lorentz invariant variables which are dot product of momenta. So we know secretly that any amplitude in any scalar field theory will always be of this sort because it has no other information. Of course, this has other. It will have other parameters. For example, if you have many scalar fields, then this will explicitly depend on masses of this, masses of the scalar fields, etc. But it will be functions of only this data. And so now the idea is that what is so special about functions which occur in physics as opposed to arbitrary function I could write down of this data? I mean, that's the question we are really interested in. And this program, which has sort of arose in last 10 or 15 years, which really tells you the following thing, that so I will give a slogan first, and I should mention that the slogan is misleading in the sense that that slogan is tested only for a class of theories, which I will specify later. And the slogan is that there exists a class of geometric convex objects in space of Xij's. So what I mean by this is that think of this variables as spanning some Cartesian space, and in that space what we are beginning to see more and more is that there are naturally, without any physics input, there are naturally some class of convex objects which are sitting, whose volume give us amplitudes of some scalar UFT. So this is a very broad slogan that has emerged out of some recent developments, and let me just tell you a little bit of the class of theories where such things have been, how these things arose. I mean, it's not something we looked for, that we didn't try to find some objects and thought, okay, volume should give us an amplitude. It's just some closer investigation of these functions revealed that they had properties which could be equated for some theories with volumes of some geometric objects. And the class of theories for which things are sort of increasingly well understood is one sort of exotic theory, which is called n equal to 4 super Yang-Mills, so that we will not worry about in this talk. And more garden variety quantum field theories which have no supersymmetry, which are scalar quantum field theories with only polynomial and non-derivative interactions. Yeah. Yeah, that's a great point. So so it's a function really, because it's a function of this external data. So it's a complex function when you think of this as an L, like you look at it as a function in the complex plane of spanned by this data. So we'll never get a number, we'll get it as a volume of so the shape, the size of the object is dependent on these variables, Xij's. There are some variables right now, and so we'll get a volume which is a function of these variables. And then you think of that as by analytic continuation function in the complex plane of these Xij's. I don't know if that answered it. Okay. Yeah. Only polynomial and non-derivative interactions. And so it turns out, and so this will be the sort of kind of a first main focus of part of our talk, that there is this very, I mean, these geometric objects are something mathematicians knew for many, many years, but no one knew why it has anything to do with physics. But it turns out that their sort of volume naturally, so their volume is some function of some, so their volume is some function of variables, but it just turns out that this volume turns out to match with amplitudes of one or the other quantum field theory, which is a kind of, I would say, striking surprise that we find. In the case of n equal to 4 super Yang-Mills, this thing is understood at arbitrary level in the loop expansion, but for the scalar field theories, we really have a control on the statements only up to one loop. So that's a caveat in the slogan that I wanted to put out there. So exactly. So it's like if you have say k scalar fields, then phi 1 to the a1, phi k to the ak. Now, this class of interactions. These are polynomial. Oh, what did I write? With only polynomial and non-derivative interaction. So these interactions, the amplitude for this will come out of this geometric picture.
So asking what is a non-polynomial?
Yeah. Well, non-polynomial could be. Yeah, well, non-polynomial would be infinite series of this, for example, like some function which is right. Right. That's non-polynomial, but derivative, of course, as you know, is if I have derivatives in the yeah. So you are right. It's a very good point that I'm assuming here that if I sum, I sum, then it's a finite sum for which I will be able to get this from the. I don't know how much time I will have, but what is absolutely remarkable is that, for example, for tree level amplitudes, if you fix the degree of, so there is one object that I will explain which is called this Associahedron, which is some convex object that just sits inside the space of Mandelstam invariants, such that its volume, if you keep doing, if you look at its, you measure its volume in one coordinate system, you get amplitude for one theory. If you look at its volume in a different coordinate system, where volume of course changes, then you get amplitude of a different scalar field theory, which is absolutely, I still feel it's a kind of a remarkable statement that one math object gives us amplitude for a wide class of theories. Exactly. For n equal to 4 super Young means, of course, polarization is never explicitly there because it's all written in terms of spinor helicity variables, in terms of gauge invariant data. So it will not explicitly, it doesn't explicitly make an appearance because in the end it's a gauge invariant quantity, and so it's no, you have included it because you have included it. It's like a volume. It's not a tensor in some space time, right? So it's, but it's gauge invariant. So then it's like a blue one. Yeah. You also have R indices, yeah, asymmetries. Yeah. So here, so I'm not sure what you mean by. I mean, the amplitude of this theory, like at arbitrary loop integrands, turns out to be volume of a particular geometric object called this amplitude itself. Exactly. So there are many ways to write this amplitude when you include everything like polarization, etc., which is in terms of either spinor helicity or momentum twisted space. So these objects don't exist in. I was giving this data because for us this data is more important. So for super Young mills, these variables are really in terms of some what are called momentum twisters. They are not coming from epsilon I dot epsilon j, etc. I don't know if that was your question.
So you know this.
Yeah. Yes. Exactly. In the yes.
And then after these y's and
yes.
y is a vector.
Yes.
Are you able to reproduce both the y dependence and the
In the amplitude case, I think so. Yes. In amplitude yes.
Would you be labeling those as well as in terms of excitation, or those are separate? What are you doing with those variables?
No. They remain separate. It's amplitude is a bit more complicated definition, but they are separate variables. They remain as a independent variable. Yeah. But in our case, we will see that because as I will show you that one of the question we have is how does theories like QED or Young mills, which has always been asked, how does it fit into this picture, or can we only recover scalar field theories, etc., from this geometric approach? So today I will at least try to convince you that there is a way to there is a way to obtain Young mills amplitude from these geometries, and in a very nice way based on earlier work which has nothing to do with this by people, physicists in early 2010, namely Kramer and the collaborators. I will explain this. So, well, no, actually this Young mills, again, I don't know how much time I have, Young mills tree level and one loop integrand, but the approach I will tell you is powerful enough that if you want to write any order loop level expansion for Young mills S matrix, I will write down the formula. For any order, you can recover it from this.
But formally, the volume is going to be infinite. You're not going to talk about a regularized volume.
No, this is integrand. It always produces an integrand. Yeah. So the volume always gives us the integrand, and
integrate, you're going to get integrate.
then we are in the usual QFT regime. Then we have to do our loop integration. That so far. That's a question for which at least I don't know if there's a very good answer. That if I do, even for scalar quantum field theory, if I do one loop amplitude, the integrand has a interpretation as some volume, but once I integrate using Dimreg, etc., I don't know if the object we find, if it has any direct interpretation in terms of some geometric object.
So background that you were saying that
Yeah.
put the coordinates of the triangles on this scalar theory.
Yeah.
So we have to say that this
No, that has not been extended to gravity. Yeah. Yeah, so n equal to 4, yeah, that's a very good point. So n equal to 4, I should have said that. It's really the most of the work has been done in planar super Young mills. So most of this geometry picture exists for planar super Young mills. Now there is a recent work by Jonathan Hen, etc., where they are able to go a little bit beyond planarity, but the geometries are different than the one that we found.
Planar, but smaller.
No, non-planar, like beyond planarity, I'm saying. So there is evidence for a non-planar, if you include 1 by n square multi-trace corrections, there is some geometric evidence, but it's not as well studied as the planar.
Even at the 10 level, you could have a coupling difference.
Yes, it's always perturbative. All this is always perturbative. Yeah, it's perturbative expansion. It's a loop expansion. So it's proofed coupling expansion and loop expansion. So,
But like small coupling or large?
so yeah, exactly. No, that's a point. Like, so I'm saying that you are doing 1 by n, and you take perturbatively also in G Young mills, small G Young mills. So the usual thing, the G Young mill square n is fixed. Yeah, that's you are asking excellent question. So of course, if I look at this, if this became large, that we don't understand how that non-perturbative corrections of that type where large n fixed G Young mills, how that comes from this picture, we don't know. I think that was your question, right? Yeah, that we don't know.
But you know for large loop coupling and planar?
No, we know for perturbative G Young mills and large n. It's our usual ADS-CFT limit. But no, we are not keeping G Young mills fixed. Large proof coupling we'll have just non-perturbative corrections in G Young mill square n, right?
Just like a string worldsheet, that picture probably will emerge.
This I don't, that's a good point. This I don't know. String worldsheet emerge means.
String worldsheet will emerge with gravity, you will not be able to, gravity, this picture has not been extended to gravity.
Well, I mean, so that's why I'm saying that the large truth limit is flat space limit, right? The gravitational correction are non-planar corrections. So non-planar, there is some evidence of.
The last truth limit is the supergravity.
Yeah, supergravity.
Large supergravity.
Supergravity, yeah, flat space, yeah.
Reproduce supergravity or say.
Yeah, this I don't know because you are saying now the dual perspective, right? This I don't. I mean, this is really we are looking at it only as the amplitude of a gauge theory, yeah, from that perspective. I think I don't know if there are people have made a connection with the dual, with the gravitational theory from amplitude, from this geometry perspective. I mean, I don't think so. Is that that's what you had? Yeah.
One question is that if you are looking at something that has not been denormalized,
Yeah.
are you allowed to talk about unitarity?
Well, no, yeah. I mean, in the sense that that's the important point, that the unitarity constraints already constrain the integrand of an amplitude, right, in quantum field theory. Because the constraints on the integrated quantity come from the constraints on the integrand.
No, that's true, but then if you did not denormalize then the partial wave expansion, the coefficient of the partial wave
Yes.
would be infinite.
I agree. Yes. So,
Then how can you
I meant something else. I'm saying that so of course unitarity gives us many constraints. So even at the level of integrated amplitude, it gives us several constraints. But the most basic constraints come out from the fact that if you look at the integrand of an amplitude and you cut it, you take any propagator on shell, then you factorize into sub-amplitudes. It's that level of unitarity that emerges from the geometry naturally, but not the no. That we don't know. No, I mean, but I think that if the integrand satisfies unitarity in the sums of factorization, then I think that with that would follow, right, after renormalization that
procedure of course.
But it goes both ways, right? The integrand didn't have the unitarity in the sense of if it didn't factorize on sub-amplitudes, then the integral will not have a unitarity in the sense of S dagger S equal to 1. So I view this as a more basic requirement. That's what you asked?
Yeah. I mean, ordinarily we check it at the level of partial wave expansion.
Ordinarily, yeah. But it emerges out of, we could relate it to the unitarity in the integrand. Right? Okay, so we will only talk about for scalar field theories, no super Young mills or anything. And in fact, the goal, I will try to convince you how we go from what we have understood so far for geometrizing these amplitudes of scalar theories to understanding amplitudes of Young-Mills, and I will focus on the tree level amplitude just for lack of time, but then I will give you results in the end for at least for one loop. We'll write down the result for one loop. So here is a basic picture. So let's start with some the space in which our geometries live. So this is a review of what is a very well-known mathematical object, Associahedron, that and I will explain what I mean by this. That naturally lives inside the space spanned by external momenta. So the only momenta I have in the game right now, and that's why we will only get tree level at this stage, are the external momenta, nothing else. So we will only have some n momenta, and they satisfy on-shell conditions. Okay, and now we know that, of course, space of all the momenta is not our physical space to describe S matrix because of the pointer invariance. So we want to impose both space-time translation invariance and Lorentz invariance. And the first thing tells us that total momentum has to be conserved. That's one constraint. And the second thing is the Lorentz invariance tells us that we should quotient this with SO31, and that means that whatever this space is, it is spanned by only some set of scalar products of momenta. Of course, all these are not independent, so we have to find only the independent set of this, what are called Mandelstam invariants. So what is the space in which our amplitudes are typically evaluated? That space I am going to parameterize as Xij, which are basically some set of Mandelstam invariants. And what are Xij? So we can choose any basis of Mandelstam invariant, and one basis which is typically useful in general also is the following. No, not right now. I was coming to that. Right now we are just saying that, I was about to come to that. I mean, right now I'm only imposing, maybe I will say it now. I mean, you're right. I mean, I was just going to say that. So we are looking at on-shell momenta, massless or massive, and total momentum conservation is satisfied, and then looking at some basis of the scalar products. And just for this is absolutely not a restriction, but I'm just going to do it because for Young-Mills we know that our external states have to be massless. So because I want to explain to you how a Young-Mills comes, I'm going to restrict this. I'm going to look at all the external momenta to be massless. But if you want, I can explain to you why that's not a restriction for scalar quantum field theories. Like whatever geometry we will find, they will give us amplitudes of theories with arbitrary mass of the external scalars also. So with that condition, I square equal to 0, I equal to 1 to n. This is a basis of all Mandelstam invariants if, so this is some old result of course in the literature, if the number of particles which is n is larger than the dimension of space-time in which we are evaluating our amplitude, the space-time dimension. So this looks like a ridiculous requirement actually because we want to evaluate amplitude for any number of particles, which means we are sort of secretly saying that whatever function we are going to get from this geometric procedure is going to describe amplitude of a theory which lives in infinite space-time dimension. Right? So you may think that this is not a physical useful notion, but for tree level amplitudes, this is really not a restriction because if you have studied S matrix of scalar quantum field theories, you know that tree level amplitudes don't know about dimension of space-time. So it's just as a parameter that comes along for a free ride. So please ask me if something is not clear. So this is related to what Arnab was saying. So we are going to do an unphysical thing where our space of external momenta, the space-time dimension is infinite, but you will see it will not matter as far as the physical answers of amplitudes are concerned for scalar quantum field theories. So, but at this stage, dimension of space-time is infinite. Okay, that's all I want to say. So, you don't have, you shouldn't believe me if I say that it should give you the right answer for S matrix, but if you meditate for a second, tree-level amplitudes in scalar theories, this never appears, so you may get a right answer. In other words, if you get a correct answer for 1D, it is correct answer for all D for scalar quantum field theory. Okay. And it's a constant, yes, exactly. And it's in you, right? Tree level, if you don't have any derivative interaction, it's only, yeah. Okay, so these Xij's, just to repeat, are these variables. And so this is some Cartesian space where each axis is labeled by one Xij. So just to give you a concrete example, if I take 4 particles, then this space is really 2-dimensional, as you can check, which is given by P1 plus P2 square and P2 plus P3 square. These are the only 2 independent Mandelstam invariants once we impose momentum conservation. There is nothing else. Because in general there are 3, of course, as you would know, but one is just determined by this. And so this space for n equal to 4 is 2-dimensional. But this space has no physics. It is a space which is simply determined by the external momenta and the fact that we are interested in evaluating objects which live in Minkowski space-time. So this space is typically called kinematic space because it has no juice right now in it. Right? It is just some Cartesian space labeled by momenta. You don't know anything about dynamics of any theory. Now I'll just directly give you a result about what this. So it's a Cartesian space. So it has at this point also actually nothing really to do with physics. But it turns out that mathematicians found that if you consider, once you take any Cartesian space and you make an association that axis of the Cartesian space is labeled by 2 variables like I and j, then you can directly realize some geometric objects in this space. So I'm going to explain, take some time to explain it. What I mean is the following. So there is something nice about Xij, so as I told before that, these are more convenient variables than say pi dot pj. And one reason they are convenient is because of the intrinsic geometry of this variable. So what I mean by this, consider a circle and put your n particles in a particular order. I am drawing some pictures which have absolutely nothing to do with physics at all. I am just telling you some nice geometric interpretation of these variables as opposed to these variables. So now you see that Xij can be thought of as, so let me put some I and j somewhere. So what is Xij? Xij is adding all the momenta from pi all the way up to pj minus 1. Which means that I can geometrically think of Xij as some chord like this. Because it's including all the momenta which lie between pi and pj. Right? Similarly, if I have, so just to give an example, in this case I have 4 particles. Then x13 is p1 plus p2 square, so it includes all the momenta from p1 to up to p3, so this is the chord, and x24 is p2 plus p3 square, so that is momenta p2 and p3 included, so that's the chord. So there's a nice chordal interpretation of these variables that is that's just right now an observation, but it's it's an interesting structure that is naturally encoded in these variables as opposed to these variables. I hope this point is clear. Yeah, exactly. Once you fix an order, only when you fix an order like this, then Xij's have a nice interpretation. Because there is a natural ordering here. You are going from pi to pi plus 1 to pj minus 1. That ordering, only when you fix this ordering, which then we can realize that as a, if I put p1, p3, p2, p4 here, then this will have no meaning. That's your question, right? So that's absolutely, yeah. So, okay, so then, but now you forget, I'm drawing here p1, p2, p3, p4, but what is important is just the labels, right, of the particles, 1, 2, 3, 4, because exactly what he just said. So x13 is a chord like this, x24 is a chord like this. Right? So now the point is that this is something that mathematicians realized, that forget about this physics interpretation of this variable, just think of this as x13 and think of this as x24. So now we have totally lost connection with physics. We simply have a Cartesian space, two-dimensional Cartesian space. The only thing I have put is that its axis is labeled by chords of a foregone. Is this point clear? So I went from physics to some space which have lost connection with physics, but then we will see that at this point when we lose connection with physics, we actually gain more connection with physics in a minute. So at this point we have no physics right now, right? It's some space. But I want you to keep this labeling in mind, because that's the key to what we are going to do next. And now here is the statement that, so because I want to do Yang-Mills, this is a lecture in its own right. So I'm just going to tell you what are the objects that mathematicians found in this space, which if you have more questions, you can ask me. One, in this space, let me draw the first object that mathematicians found in this space. And when I say mathematicians found it, they found it using some structures in mathematics, in representation theory, which is for some other reason altogether. But here's the first structure they found, which looks kind of trivial. They found a line. I will explain how they found it, which satisfied the following equation, where C is a positive constant. What do I mean by they found this structure? So if I focus on this structure, it has three ingredients, two vertices and a segment between them. So let's forget about the slope of this line for a minute. Let's first look at just what this object contains. It has two vertices and a segment. Now, what has this got to do with what we have done here? And that's the following. Think of, so I'm now going to, instead of circle, just drawing it as a foregone, just for convenience to draw. You see that this foregone can be split into triangles in two ways. This is one way to split it into a triangle, and this is another way. So there are only two ways that we are splitting into triangles, and think of this one way to split into a triangle as just one object, like one point. Now, how do we go from here to here? What's the common between these two? Common between these two is no splitting, right? Is it clear what I am saying? This is splitting foregone into two triangles. This is also splitting foregone into two triangles. But the only commonality between these two is no chords, right? Because there is nothing else, right? So that means think of this as one. Every time you fully triangulate a foregone, think of it as one point. This is also another point because you have completely triangulated. But no triangle means join it. Okay. So this object is a purely combinatorial object. It has nothing to do with anything. And this object is called one-dimensional Associahedron. Okay, so far we have not connected to this line, because this line is, I can draw a segment like this in a two-dimensional plane in infinitely many ways. But I have now drawn it in a specific way, which I will explain in a minute. But let me expand on this definition a little bit more for 5 points instead of 4 points. That will make it a bit more clear of what these objects are combinatorially. So please ask, okay, if something is not. No, that's a very good point. X13 is just a label which tells you that there is a chord. It's not length or anything. Yeah. So we are labeling X13 is a Cartesian coordinate. We are just labeling it with a chord data. That's it. Yeah. That will be important when we do physics, not here. The point is that we are saying that, okay, if you consider, let's take an example of n equal to 6. Then how many chords we have? We have x13. Let me write all possible chords. x13, x14, x15, x24, x25, x26, x35, x36, x46. Why did I not? Is it okay? There is no adjacent entry here, right? Because all chords must not be. Is that clear? Yeah. These are 9. but the number of independent Mandelstam invariants in 4 dimensions, if you have 6 particles, is 8. Because these 9 variables satisfy a highly complicated nonlinear determinant constraint. So that means that we should be at least in 5 dimensions for these to be independent. If you go to n equal to 7, if you're in 5 dimension, then the Mandelstam will become again dependent by one condition. So we should be in dimension 6 for them to be independent. Otherwise, this picture that I'm associating a 9-dimensional Cartesian space to this is no longer valid. Right? That's my basic point where I went from physics to maths, that I'm labeling a Cartesian space with these, right? So they have to be independent, which is not true for any n. Once you go to fix a dimension, this is not going to be true beyond some n. Okay, and this is important. This becomes important later, but yeah, we can discuss this if you have time. I don't know if it exceeds today because I'm here a week. We can do another.
Yeah, we can continue on.
So I will not rush then. Okay, fine. Okay, then please ask me more questions. Sorry, I just thought we have 1 hour, so I tried to kind of summarize some things. Okay.
Historically,
Yeah.
Historically, this Associahedron was discovered by mathematicians before timing physics, or?
Yeah, this was discovered by Jim Starship in 1964. Yeah, so it's of course this was a golden period for analytic S matrix program, and it was also golden period for discovering class of these combinatorial geometries, but that is a coincidence. Yeah. Yeah, so let me give another, so this is a specific simplest example of this one-dimensional associahedron, which is just a combinatorial object like this. So let me give one example which will make it absolutely clear what these are. So let's take a 5-gon first. And we want to follow the same logic. We want to start triangulating the 5-gon. So of course we need 2 chords, right? So this is one triangulation of a 5-gon. But I can draw, actually there are 5 of them, as you can notice. I can draw another one where I will keep, let's say, 1, 3 fixed, and I change this to. Let me draw all of them just for this one example. Then I can draw. Sorry. Then. Oops, I should have one more. So you see now again what has happened. Like, now let me draw the combinatorial object corresponding to this. So you see that this thing is one triangulation, which, as we noticed here, we associated to a triangulation a dot. So again here I am associating to this triangulation a dot, but this triangulation is labeled by chords 1, 3 and 1, 4. Is that fine? And similarly, if I look at this one, it's 1, 3, 3, 5. This is 1, 3, no, 2, 5, 3, 5. This is 2, 4, 2, 5. And this is 1, 4, 2, 4. And now you notice that if I look at these 2 dots, here the only thing common between them was no triangle. But here the thing common between these 2 is 1, 3. So that means that these 2 dots are joined by, but what is common between all of them is no triangle. So that means that, so here let's look at this picture for a minute. There is a one-dimensional object whose interior is labeled by no triangle, and its boundary, which is 1 dimension lesser, is labeled by complete triangle. Let's look at it same way here. The object is 2-dimensional, which means the 2-dimensional part is labeled by no triangle. If I go to its boundary, which is 1 dimension lesser, which is this one, it is labeled by 1 chord, which is in this case 3, 5. If I go to the boundary of 1 more dimension lower boundary, it is labeled by 1 more chord. Right? So this object is what is called a 2-dimensional associahedron. And now you can immediately check that you can easily generalize this to any, you start with any n-gon, start triangulating it. Complete triangles are vertices. If you remove one chord, you get a boundary which is one dimension higher, like an edge, then 2 dimension higher, and then the higher dimensional object has no triangles. Is that clear? So and we can count dimension also. So this is a 1-dimensional object when we started with a 4-gon. This is a 2-dimensional object when we started with a 5-gon. And you can easily convince yourself that if you start with an n-gon and you triangulate it, you develop an object which is n minus 3 dimensional. And this is what Associahedron found for some completely different purposes. I heard that he had hard time getting this published because mathematicians didn't find much relevance at that point in his discoveries. So now, but these are just abstract geometries, right? They are not like, we are not embedding them in any Cartesian space, right? The definition of them doesn't tell us where they are sitting. But of course, if I give you a pentagon, I can draw it in a 2-dimensional space or 3-dimensional space in infinitely many ways. That is not there is no constraint. Now it turns out that now this I will not go into detail unless you really want me. Just this fact that you are switching 1, 3 to 2, 4, this object generates some particular algebras which are called cluster algebras, and representation of the theory of that algebra naturally tell us a way to realize these as concrete geometries in Cartesian space. So it is some developments in representation theory which told us that if I don't use any other input except what this algebra generated by this chord is giving me, I get a unique drawing of this with at a 45-degree angle. So this part, it is not that hard. I can explain, but it will just take me 5 or 10 minutes more. But this part of drawing an abstract polytope like this in a unique way, like this, is gift of what is called, the name of the entire branch of mathematics is called quiver representation theory. And it's a very simple actually thing to understand. Maybe I can spend some time later to discuss it. But I hope you appreciate the point. What I mean by this is, if I just gave you this thing and I told you draw it here, what will be the most general way you draw it? Alpha x13 plus beta x24 equal to gamma. Right? This will be the most general, at least linear way to draw this. So it is the other development in maths which tell us that alpha is 1, beta is 1, and gamma is arbitrary, but positive. Okay, so the shape of the geometry is fixed by some developments in mathematics which is not coming from physics or anything, just something else. So the idea was, mathematician motivation was the following: if you give me alpha equal to something, beta equal to something, means you are putting it by hand. That alpha beta is divorced from this combinatorics. Is there enough in this triangulation itself that fix alpha and beta? And then they found that there is enough in this structure itself that fixes alpha beta without we putting it. Any other alpha beta, we are putting it by hand. Okay. And similarly, if I look at this 2-dimensional associahedron, it is drawn in the following way. So let me draw it concretely in the Cartesian space. Yeah, please. That's a very good point. So if once I have fixed my x13 and x24 as the chord labeling the dissection, the coordinates labeling the dissection, there is no if you only use this particular branch of mathematics, alpha beta have no other choice possible.
It's a 1D thing, or?
No. If I only use this, of course people have found other consistent way to. So there are two problems. One is, take this Associahedron in any D of any dimension. Now you ask, can I always consistently draw them as convex geometry in some Cartesian space? This is a hard problem because I'm going to show it for any n. So I have to find coordinates for every vertex, etc. This can be done in many ways. This itself can be done, but that's a geometry problem. That consistently I want to put any Associahedron in a Cartesian space such that it should always be convex. So this has been done. This work was done by Postnikov some years back, which is a nice. He did it not just for this geometry, but a wider class of geometry. But your answer was first given by a person called Laddha, who gave just a construction of realizing one way all the Associahedra in Cartesian space. But that requires input is like, the input is, you are finding some realization, whereas I am saying that this one is, everything is combinatorial. This one is something combinatorial. But what is interesting is that what is in some sense most natural from math perspective is one that finds direct use in physics. That is not to say that this would not have use in physics, but we don't know directly right now if these geometries give us any amplitudes. Convexity is related to unitarity, but it is not that everything convex will always give you. We don't know if these other shapes of this associahedron, they are giving us amplitude of some theory. They may, we just don't know.
Probably will, because
they're convex.
This is a time order correlation function.
They may.
They could be retarded.
Absolutely, yeah. That's why I'm saying that we just don't have a direct dictionary from these two physical quantities right now. But if you ask me honestly, it must be there. It's just, you know, if you look at this construction, they are ingenious in the sense that you have to find specific vertex coordinates, etc. Right? Some algorithm you have to give for any n. That's not easy. So they give some recursion, given some embedding of 1D, some 2D embedding, etc. But the data is not coming only from this combinatorics of dissection. It's more than that. Just to give you this realization of the two-dimensional associahedron in this way. So the space, this kinematic space for n equal to phi is 5-dimensional. That you can immediately see, right? Because how many chords are there? Possible chords are there. 1, 3, 1, 4, 2, 4, 2, 5, 3, 5. No other chords are there. So these are just this is a 5-dimensional space. And it turns out that if you follow mathematicians, then there are following ways to draw this inside this 5-dimensional space. So this space is x13, x14, and all the rest. So I'm just drawing 5-dimensional space like this. And in the case of 1-dimensional associahedron, there was a unique drawing. Now it turns out that the drawing is not quite unique. There are some ways to draw it, but as we will see, one remarkable surprise was that all the drawing gives same amplitudes. They don't change the amplitude. So, but let me tell you what the drawings are. So one possible drawing is the following, and I will tell you what the other ones are in a minute. So this is again following quiver representation theory, that we find the following shape. So this is okay. Maybe yeah. Sorry. Let me write the equations first, like I wrote here. Maybe that's more instructive. The equations are. So you see, if you look at these three equations, you see that one can solve for x25, x35, and x24 in terms of x13, x14. Okay. Again, C's are arbitrary positive constants, just like the previous one. So now you can see, right, that why, if these equations were given to me, I could draw this as a geometry in the plane x13, x14, right? It's immediate, right? Because I could solve for other variables in terms of 1, 3, 1, 4. And when you do this, this is the realization you find, that this boundary is x14 equal to 0, this boundary is x13 equal to 0, this boundary is x35 equal to 0, this boundary is x25 equal to 0, and this boundary is x24. And this slope is 45 degrees. Okay, I have just drawn this in the 1, 3, 1, 4. This is not something complicated. Now what are the other ways? You just permute these labels. Instead of 1, 3, 1, 4, you look at 2, 4, 2, 5, 2, 3, 2, 4, 1, 4, for example. You write this equation by exchanging 1, 3 with 2, 4 in a systematic way. This entire polytope will be rotated and it will sit in the 1, 4, 2, 4 plane. But the shape will not change. Okay? So so what I've drawn here, if you just relabel the axis instead of 1, 3, 1, 4, 1, 4, 2, 4, and keep everything same, that will be the associahedron in the, that's a different way to draw this associahedron. So unlike in the 4 part, in the n equal to 4 case, there was one drawing. Here there are 5 C2 drawings. Is that clear? Is it clear? Okay. No, not 5 C2, sorry. There are 5 drawings. I apologize. 5 drawings. So the 1314, 1335, 2535, 2425, 1424. You could choose these axes to be any of them, any of these 5 pairs, and you get this associahedron. So there are 5 ways to draw it, not one way to draw it. But they are all, as we will see, physics-wise, they are all equivalent. They don't give different physics. Okay. And so now this construction can be done for any n. and I will just write down the, That's a very, very good point. Then I would say that it's not, because right now what we will find from associahedron are tree-level amplitudes which are planar in the sense that their ordering is fixed, so there is no crossing. So yeah, we can talk more. I think that if you ask me how would I get 1 by s plus 1 by t plus 1 by u from this geometries, there is a way to get it, but it is one has to, yeah, maybe I can tell you privately. At the 0th order crossing, right? I mean that itself doesn't come out of only this, but it's more.
But if you have colored scalars, you will only have 2 channels.
Exactly, there is no crossing. That we get, but that's not crossing.
No, but it's permutation invariant at SN.
But that's not crossing.
No, I mean in the complex S plane it is. I mean,
It's just permutation, right? I meant crossing. Yeah. Okay, fine. But I just meant that full crossing symmetry in the sense of.
yeah, but you don't expect full crossing symmetry because they are different amplitudes. They are different.
Okay, so you're saying because you get only planar color ordered amplitudes? Yeah. Okay. Yeah, you're right. Okay. But if you want a fully crossing symmetric function, which is 1 by s plus, forget the amplitude part, just fully crossing symmetric function, that doesn't come out of this directly, but it does come out with some.
This is the structure of the Venetian amplitude.
Yeah. Okay. Fine. Yeah. If you ask like ordinary phi cube tree level amplitude.
No, that I agree.
Yeah. But right now we don't have color or anything. Because right now, of course, we don't have any amplitude. Right? We have disconnected ourselves from physics right now. And these variables, I want to emphasize that at this point you should not think these variables are related to our Mandelstam. Think of them only as Cartesian coordinates, because that's where the rich physics emerged, not by. Yeah.
So, subject to these constraints.
No, I will come to that in a minute. So these constants have given us some drawings. So right now this is what we have. Now I will tell you how the volume emerges. Okay. So maybe I was saying something. Yeah. So let me write just if you think I am sort of exaggerating, then one can do it for any n. Let me write down the equations for arbitrary n, which was proved by mathematicians that they give us consistent drawings of these associahedron. So if you take any n, which means I have an n gone, and this mathematicians tell us how to draw the corresponding associahedron, which is n minus 3 dimensional. In a space which is parameterized by x13, x14, all the way to x1 n minus 2. So the full space of chords is larger, right? Here, like the full space of chords is 5-dimensional, but the realization of this associahedron is in a 2-dimensional subspace. Similarly, in the same way, for arbitrary n, the full space of chords is of course x13, x24, everything, but fix the maximal set of non-intersecting chords. And look at that plane. So that's the plane x13, x14, blah, 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 x1 n minus 2. And in this plane, there is a fixed realization of this n minus 3 dimensional associahedron, and that is given by equations which are direct generalization of these equations that you can find. So I just to convince you that this is not some complicated subject, it's linear equations, and that also someone gave us. We didn't have to. Although I should say that these equations were first discovered by physicists from some. Their goal was that what should be the slope of all these things, so that the volume of this somehow is related to S matrix. So there was some physics motivation. They found these realizations, these equations, and then mathematicians said, well, no, but even this quiver theory gives us exactly these equations. So this is another nice surprise, but because it was first realized by physicists, these particular drawings are called ABHY associahedron. In the name of the physicist who discovered these drawings. This is Arkani Ahmed, Bai, K, and Yoon. And the connection with this quivers was realized by 4 mathematicians. somehow their name, all their name starts with P only. I don't know why. So this is the math. This paper came out in 2017, and this came out in 2019, and they showed that that these equations were not only from physics, but even whoever told us that same equation should be used.
Sorry, I mean, just so that I remember, the reason these constraints came in the quiver
Yeah.
was exactly what you just tell me one more.
Yeah, that I didn't explain. Let me explain. Maybe it's like 5 minutes. Yeah, no, I can explain. It was just so it is related to some algebraic construction, but I'll give you the final algorithm that arises, which is easy to understand. So let's take n equal to 4, and let's draw the combinatorial geometry first. So as we saw, right, it's this, and this one has two. This dot is this, and this dot is this. Now this entire quiver picture does the following. It says that, well, so now this I'm bypassing the motivation of why these things are coming. Consider dual, let me call it dual vertices, 1 prime, 2 prime, 3 prime, 4 prime, like this. And now consider the following paths, which go from 1 prime to 3 prime, 2 prime to 4 prime, like this. And now inside each triangle, fix an orientation. So now you see you got some cycle inside each. So fix orientation. You have to just be consistent, but you can choose any orientation you want. So let me choose clockwise. You can choose counterclockwise. Now you see that if you look at this path, 1 prime, 3 prime, that is out at this vertex, both the chords are outgoing. So that means that I can associate to 1 prime, 3 prime a slope. Let me associate an index to it, which is +1. But if I look at 2 prime, 4 prime, then both the arrows are incoming. So now I can associate a label to it, which is -1. And so now the logic of the equation was that the x1, 3. So this is what the fact that these two are, this is minus of this. That's what fixed the equation that we found. I don't know if that helps you. No. They are imposing because these paths, you see these paths, you can compose them. So this, this is a path from 1 prime to this vertex, then vertex to 3 prime. So this composition of these half paths form an algebra. Now they wanted to find some representation of this algebra, and that representation was dependent on this discrete data that we are finding. And so this data is purely combinatorial, and it is this data +1 -1 which gives us alpha equal to 1 and beta equal to 1. But it's just this data. So to give you one more example, which may be even more clarifying, because n equal to 4 is slightly pathological because there is no normal. Like this is a vertex, so there is no normal to this vertex. But for n equal to 5, it's slightly better because we saw that the associahedron itself is a pentagon, right? Itself is a pentagon with vertices labeled by 1, 3, 1, 4, 1, 3, 3, 5, etc. Right? And this one, as if you remember, is labeled only by 1, 3. So now the point is that if you now look at it's the same logic you follow, the same logic. So let's fix one dissection like this. And now let's again do the same thing, 1 prime, 2 prime, 3 prime, 4 prime, 5 prime, and draw the same thing we just draw. And choose an orientation. So I will just choose clockwise again. And now you notice that 1 prime, 3 prime is again outgoing at 1, 3, and it is not at all intersecting 1, 4. So I'm going to associate numbers to it, 1 and 0. So what are these numbers in reference of? It's in reference of 1, 3 and 1, 4, because that's fixed for me. So this is the number I'm associated with 1 prime, 3 prime. Okay. Now consider, let's look at some other, let's say 2 prime, 4 prime. So 2 prime is converging at this vertex, and it's outgoing at this vertex. That means that with 2 prime, 4 prime, I can associate the numbers which are -1 and 1. Right? Same logic that I used here. Let's look at 2 prime, 5 prime, which is more interesting case. So it's this is the path. So it's at this vertex both are coming together. So that's -1. At this vertex there is no direction change. So we put 0. So now you see that in the 1314 plane, so what are these numbers signifying? These numbers are simply signifying the normals to the faces which are, so and now I'm telling you how the drawing came. So if you look at this drawing, you see that this is x25 equal to 0 and this is x13 equal to 0. So the normal to x13 is this way and the normal to this x25 equal to 0 is this way, which are opposite, right? So you see the 13 we associate a number which is 10, 1 prime 3 pi 10, and with 25 we got a number which is -10. So and precisely those are the normals. We found, right? I mean, I think I got convention ulta. This should have been minus, this should be plus. But you see the difference. Is a slope, and so that's why it's -1. So each this data gives us the corresponding normal to the faces, and that gives us the drawing. So that's the way that it came from. So, but this is remarkable, right? Even if you don't know anything about mathematics, this is some combinatorics data. So why should this have anything to do with physics is a surprising fact. Yeah, but yeah. Okay, so now if you are convinced with this drawing, now we can start making connection with physics. We need one more math ingredient. So Anila, you tell me how much time, because we haven't even done scalar field amplitude yet, but okay, you tell me when, because we have next week, so we can spill over, no? Okay, so then we can, you tell me, yeah.
So the reason why, at least this was my understanding, that Nima wanted to replace the notion of locality and unity.
I will come to that, yeah.
Something geometry.
Yeah.
And does that actually buy you anything, or is that some?
Yeah, I think it buys, as you will see in a minute, even in scalar field, it buys you a lot, even for tree level. If I ask you what is common between S matrix, tree level S matrix of a massless pi cube theory and a theory which has two scalar field, one massive massless and the Yukawa type, phi 1 square, phi 2 type coupling, answer is nothing, because they are different theories. And if they both come from volume of a same polytope, then that shows some kind of a universality between. They are related means they are all coming from geometry of Associahedron, all of them. All the ones which have non-derivative polynomial interaction, they all come from this one single geometry. So I think structurally it's an interesting, and I'm giving you example at tree level, but whatever I'm saying is verbatim true for one loop integrands for class of polytopes which also came from some other math. So I will. But psychologically, I think what's important to keep in mind is that we are not looking for, it can happen that we find some polytopes which don't give us S matrix. So right now we are saying that, look, these are polytopes which are naturally sitting in some Cartesian space. So far no physics. Once we start associating x13 with p1 plus p2 square, do we recover any physics? If we don't, we don't. So we are not looking for some object which gives us locality unitarity. These are just naturally sitting in some boring space, and that space has some identification with Mandelstam in the terms of label. That's it. Right, that's
very surprising connection, because
yeah.
No seems to know about.
No, it doesn't.
What space time you are doing that.
No, yeah, connection at all. Yeah, only it's that asymptotically states are parameterized by momenta. That's it.
Yeah.
Yes.
But this is the physics interpretation is that of scattering amplitudes in flat space.
Yeah. And if you look at it as a step-by-step procedure, asking I will tell, so this is a very good point. So what do we start with? We start with dissect chords in a polygon. That's our starting point. Then these chords in polygon give us some combinatorial geometry that we call associahedron. Then we use some math theorems coming from QoR representations and give us convex ABHY, which are drawings of associahedron. So far there is no physics. It is at this stage that once we start identifying the small xij with Mandelstam, then physics may or may not emerge at this stage. So that's it's like a bootstrap in that sense, right? Some geometry which gives us amplitudes. Then we could say more. I mean, what happens if I break this associahedron into 3 pieces? Does each piece give us something?
Is there some similar parallel development for say amplitudes and
There is, yeah. But those are different. These are called cosmological polytopes. Yes. But I think they don't. I mean, yeah, I don't know much about. I mean, my knowledge of that is like very superficial. But they are not. So again, they are basically you have an amplitude. You look at it and you say, look, its singularity is like this, like this. So maybe we find the geometry. But what I'm saying now is not that. Because I feel that would be a little bit useless program in QFT. That you tell me, okay, for massless 5 cube you have a geometry, but do you have something for 5 4, or do you have something for 5 1 square, 5 2, 5 3 square? And if I don't have, then it's a bit strange program, right? So I want to find geometries first, which are naturally sitting without physics input, and then see whether they have anything to do with physics, rather than other way around.
going back to the statement that you just made that there is apparently different theories which are.
I will explain that.
But so the importance of that statement is because there is some duality that links these theories, or what?
There is a coordinate transformation of this that links these amplitudes. So if you do linear coordinate, I was about to explain, but since you're asking, I'll just say, if I just do identification of small x13 with Mandelstam x13, which was p1 plus p2 square, I get amplitude of some theory. But if I say that x13 is some alpha x13 plus beta x24, and x24 is gamma x13 plus delta x24, even linear diffeomorphisms, because this is some Cartesian coordinate system, right? What is it? But on the capital X, there is no metric. So this is where we are putting an additional input, which is not coming just from this structure. So this diffeomorphisms already give us. So this one will give us amplitude from some scalar theory with only one scalar field. Depending on how I choose these parameters, I get amplitudes with different scalar with different mass, etc. So that's. But the math object up to this point is this is the same object, right? So its volume in different coordinate system are giving an amplitude of different theories, but the underlying object is the same.
But the singularities will also be fixed by this alpha and
Yes,
beta,
yes.
and the result of which we can go from one spectrum to another
Yes,
spectrum.
yes. And also, sorry, I forgot, and some, of course, and some, maybe some.
In some sense, we are talking about duality.
Yeah, it's some diffeomorphism, and it's we don't understand implication of this. Like, what does this mean? That your diffeomorphisms of this coordinate system give us relation between amplitudes of unitarily inequivalent. Yeah, with different spectrum. Yeah.
So, can the volume of the Associahedron tell me something about the volume corresponding to the original polygon from which it was constructed?
No, that's a very good point. But I mean, I should have said this before. The original polygon is not a. It's just it's what we call abstract polygon. It's not drawn anywhere. It has no volume. I mean, we are not putting its length or anything. It's just combinatorics.
I understand that.
Yeah.
The question that I had in mind is basically in case of group integrals.
Yeah.
Polytopes from the treatment type.
Yes.
And I was wondering there is what where you can construct an Associahedron that structure corresponding.
That's an excellent point. So I don't know if there is a student here who tried to ask this question from IISc, that some geometry, but I think it was not related to is it here? Someone is here or no?
Was it Ratan?
Not Ratan. No. Ratan's junior, I think. I forgot. Yeah. But I think the geometry he found are not associahedra. They are some other polytopes, I think, in terms of the Schwinger parameters, right? So I think he is the only attempt I know who tried to do this, but I think they were not associahedra. I'm forgetting. I think they were. Okay, we can talk more. They are something called Newton polytopes. So yeah, but they are not associahedra.
I mean, the Newton polytopes would play the role of this original abstract polygon picture. So
Yeah, that's yeah. Okay. No, now I appreciate the question more. Yeah, I have to think about this. No, I understood the question. Yeah, again gives you the yeah. I understand. I need to think about this. I think you know this more than me. I gave a very superficial answer. No, you are right, because Newton polytope can be Optenbaum, this associahedra equation, etc. So I think you have some direct connection in mind with the associahedron, right? If I understand correctly. By the way, I should say one thing, that was for loop. You have already done loop integration. in that picture. You have not done the Schwinger integration, you have done loop integration. So there the geometries that you are getting are not loop integrand geometries.
No, they are loop.
Yeah, we have done loop integrals. We have only not done Schwinger integrals. Right? I mean, this is a usual Schwinger, right?
No, I just there are no momenta involved. It's just a Riemann of.
Exactly. We have done the loop integration. We have finished loop integration. That's our usual Schwinger. I'm saying. I'm not saying anything more. Right? You start with your one Feynman graph. You write the loop integral, write into Schwinger parameters. Now you can do loop integration without any problem because it's simple. Then what you find is only Schwinger parameter integral of same meaning, and then you have the structure is in terms of what are called semantic polynomials. Yeah, that we have not done. That integral is there, but that integral has no direct connection with the loop integral. No direct connection, right? Loop is done, right? It's integrated over. Right, yeah, but the loop, when we say loop integrand, we mean this, right? Right, this, some external momenta and loop, right? This is a interpretation in terms of geometry of this volume of some polytope in the way I am describing. Yeah. Whereas when we do the Schwinger, we get, if you have say n edges, where f and d you are the semantic polynomial, and now you are describing how to obtain this from Newton polytope. No? Okay. I thought that was the Ratan. Okay.
Basically, the volume that you construct from the deformancy polytope.
Yeah, from this one, no?
That is basically
Yeah, okay. This is in the, you can go to Lee Pomeranski, it's f plus u by u, whatever, yes. Yeah.
So, what I was saying that the volume of that person,
Yes? Yes. I understand. I was just saying that volume interpretation is in terms of some, okay, Lee Pomeranski also, in terms of the semantics.
Yes.
Whereas here, the volume is a function of P1 to Pn and L.
Yes.
That's all I'm saying. So that is why I'm saying the direct connection, I don't know.
Okay.
Right? Because here L integration we have already finished.
Yeah, I was not even trying to
Relate them.
connection with that instrument.
Oh.
I was not trying to.
So then what are you saying that if I take this and then it has anything to do with associated?
So, no. So basically, you have that Riemann polytope.
Yes.
You are labeled by the
Yes.
Now you can triangulate them.
Yes.
And those indices carry information about the kind of analytic structure that you have.
Yeah. This I completely agree. Yes, absolutely. Yeah.
I was wondering that this might not make any sense to you, but in principle,
No, I just don't know. I mean, it may be correct. Yeah. Yeah.
if you try to construct an Associahedron corresponding to the Newton polytope, you can.
Yeah, that you can. You can. There's a prescription to any from any Newton polytope. Yes.
So, I mean, I was
No. Okay. I think we need to think. I think there's a lot of stuff in what you're saying. But I don't think anyone has looked at this angle yet to the extent I know, except maybe your senior or some.
basically it becomes easier to calculate the volume of the Associahedron corresponding to the Associahedron
Yeah.
and translate it back to an information of the volume.
Okay, that's an excellent point. Yeah, now I appreciate your point. Yeah, so I think this may be very much possible actually because there is a direct algorithm to go from Newton polytope to associahedron, and you are saying now that for associahedron volumes we know how to construct. We have closed form formula. So that's what I think that's your idea, right? Okay. So I think you should just explore it. I don't think it has been explored.
Any one of these lines of general questions in this talk?
Sure. Yeah, okay.
So, is the philosophy that you
And what time? I mean, time. Chair has the time constraint. Right, chair. Oh, is the chair what itself he hates?
It's not an armchair. No, so the philosophy is you have a similar formula without any loop integral for the tree level, and then a similar
For the integrand, yeah.
for the integrand.
Yeah.
So the tree, so far as unitarity, perturbative unitarity is concerned,
Yeah.
this tree level is going to talk to the one loop through the optical pair,
Yeah.
right?
Yeah.
So how does it work out geometrically?
Yeah, it's beautifully works out because the polytope that gives us whose volume gives us this, its boundary structure is intimately tied to the associahedron. I have to explain more. I mean, So when you go on shell, it means that we are going to one of the boundaries of these polytopes. When you go to boundary of the polytope corresponding to this guy, that is intertwined with the associahedron itself. And that is just part of.
And that should be sensitive to space-time.
No, again, because these are scalar integrands, there is no dependence on space-time dimension. Right?
But unitarity is sensitive even at one-group level to the space-time dimension.
Not at the level of that, the integrand, when you cut on shell, you get sub-amplitudes of the integrand. That is not sensitive. Yeah. By the way, I should say one thing based on your, again, I think you would know it very well that everything, so again, because we are talking more generally, the data that give us these drawings are these normal vectors. So these normal vectors, let me label them. I mean, in math literature, they are called G vectors. So for this labeling is again the face with which it is normal. So for associahedron, we have 5 normal vectors, which give us normal to the faces of the associahedron once we draw it. Now you can ask, okay, these vectors, they are some, they are vectors in this Cartesian space, right? Because that's how we draw we got the components, right, in this space, 1, 0, 1, minus 1, etc. You can ask, okay, are there some forms which are dual to these vectors? Again, this is some question mathematicians ask for some other reasons. Are there some form which is such that when you feed in, which is also labeled by 2 indices, which when you feed in this, you get delta ik, delta gl. And if you can find, so there should be a form which only clicks on alpha 1, 3, which only clicks on g1, 3, 0 and everything else, alpha 1, 4, 0 and everything else. And existence of this form was known from 2017, but recently Nima and the collaborators gave closed form formula for these forms. Now, once you give me this form, alpha, look at the following construction for tree level amplitude. Again, I am talking generally, so I hope we can resume more systematics next time. So consider, I should not say amplitude, just consider following partition function. Formal partition function. I will explain why, in what sense these are functions of t in a minute. What do I mean by them being functions of t? Well, in this case, they are functions of 2 parameters, right? Alpha 1, 3 is a function of 2 parameters, t1, t2, such that it is 1 on 1, 0. But if you take any other choice of t1, t2 corresponding to the other 5, it is 0. That's how alpha is determined. So you take this thing. There are closed form formulas for these alphas. I'll give you one concrete example. If you take n equal to 4, then we have only one. We have only one parameter, and because it's going to n minus 3, n is the number of labels we have, and we have minus alpha 1, 3, x1, 3. Minus alpha 2, 4, x2, 4, where alpha 1, 3 one can show is given by max of 0t, and alpha 1, 4, which is a function of t, one variable, and alpha 2, 4 is t minus max of 0t. Now you substitute this here and you integrate, you get, it's just some now dumb integration, you get 1 by x13 plus 1 by x24. And this gets generalized. So you went from, I was just, this connection to what you said, even though it's a very naive compared to what you were suggesting. I went from these G vectors to these alphas and to some Schwinger expression for tree level amplitude. For the full amplitude, not for like a one Feynman diagram. And this has been shown to hold to all ordinary loop expansion in this amplitude. So there is a Schwinger parameterization not of one graph, but for the full amplitude. But that comes from these G vectors. But whether that is related to associahedron, this is the direct connection I know from associahedron. But I think you had something deeper in mind, so we should definitely discuss it. Yes, exactly. That's what you yeah. Okay, so you tell me, this was all detour. Yeah. Yeah. Then it will not be unitary. So yeah, that's a very good point. So I don't know about complex coupling what it does, but I can give you one example of. Yeah. But I can give one example where. Okay, let me give the following example. If you consider lambda, if you have only one coupling, right, only one, then because in tree level amplitude some power of this comes out, so we never see it in the tree level amplitude. But suppose I have two couplings, I have this and say, yeah, or say let's say this is some massless scalar, then you have some massive scalar, and then you have some, just as an example. And now you start making some of this negative, such that for a combination they violate unitarity. Then what happens is that these shapes of these polytopes, which are always convex for positive lambda, when you make some of them negative, they start changing and they become like this. And they become like this when this negativity implies loss of unitarity. So the loss of convexity, I am not answering your question because this is not complex coupling, but at least the loss of convexity is tied to the loss of unitarity, which may come from relative, there's some coupling becoming negative. But when it becomes complex, I don't know like what implication it has, because here we are assuming that we are drawing these polytopes in the real space, and this lambdas feed into the slope and the intersection of these lines. So we are assuming lambdas are always real. So there is some connection of seeing loss of unitarity with convexity, but not in the sense of complexity. Yeah, okay. So sorry, we got into some digression. Tell me when to stop, we can resume then.
Maybe we can stop now, and because it's 4:30, and then we can resume. I think we have to find out whether speeds when resume is available. So Monday we can continue either here or there, whichever is available. You will know.
Okay, so sorry for the detour. Yeah, okay.
We are making full utilization of it.
Yeah, thank you.
Underpaid theoretical